Welcome to This Explainer. If you've ever looked out the window of an airplane and just marveled at the sheer force it takes to get a massive metal tube off the ground, well, you are in exactly the right place. Today, we're demystifying the incredible machinery that keeps aircraft safely suspended in the sky, putting the emphasis squarely on the power plant, the actual engines that make modern aviation possible.
It really is a fascinating physical puzzle, right? What does it actually take to safely push a multi-ton aircraft through the sky? Today, we're going to look at two completely different mechanical solutions to the exact same physics problem: overcoming gravity and drag with absolute, unwavering reliability. We'll see how aviation has evolved to conquer both the low-altitude skies and the high-altitude stratosphere.
All right, Section 1, the heart of the aircraft. Let's dive right in by establishing the baseline requirements that every single aircraft engine has to meet. We're talking about the absolute non-negotiables for any flight. The engine has to be incredibly reliable under wildly varying flight attitudes and some pretty extreme weather. It demands serious durability to run for long periods between overhauls. We also need operation flexibility, so the ability to run perfectly smooth from a quiet idle all the way up to full roaring power. And doing all of this requires an incredible feat of engineering to balance fuel economy with enough raw, compact power to actually lift the plane.
And that brings us to a huge metric: specific weight. Think of it kind of like hiking with a really heavy backpack. Every single excess pound of weight carried by an engine actively reduces the useful load and performance of the aircraft. So, for decades, engineers have literally been in a relentless, nonstop fight to lower this specific weight, all while keeping the engine from tearing itself apart.
Moving right along to Section 2, the reciprocating workhorse. Let's explore the undisputed champion of low-speed, highly economical flight. Check out this typical four-cylinder opposed engine. You notice those thin metal fins all over the cylinders? Well, since piston engines cool themselves by transferring heat directly to the surrounding air, those fins are there to drastically increase the surface area. Without them, the engine would literally melt itself during operation.
Internally, this machine operates on the classic four-stroke cycle. You can think of it like mechanical breathing. You've got the intake of the fuel and air mixture, the compression of that charge, the controlled burning that gives you the power, and finally the exhaust stroke to push out the burned gases. The engine goes through these four distinct steps several hundred times every single minute, firing in a precise sequence to keep everything turning smoothly.
What's really cool here is watching the literal conversion of energy. As those expanding gases shove the pistons down, that straight line back and forth motion is perfectly timed by the connecting rods to convert into the rotary spinning motion of the central crankshaft. That crankshaft is basically the backbone of the entire engine. It absorbs all the work from the cylinders and transfers it directly out to the propeller.
90%. That is a massive number. It represents the mechanical efficiency of your average reciprocating engine, meaning even after you account for all the friction between those rapidly moving internal parts, an impressive 90% of the power developed inside the cylinders actually reaches the propeller shaft to do the hard work of pulling the plane forward.
But, eventually we hit a physical wall. While reciprocating engines are absolutely perfect and highly efficient for cruising speeds below 250 miles per hour, they start losing their edge as we push the envelope. Once you get above 400 miles per hour, propeller efficiency just drops off. And that brings us to a completely different mechanical solution.
So we end up with this really stark contrast between our two dominant power plants. On one side, the highly economical, low-altitude piston engine. On the other side, the high-altitude, high-speed dominance of the gas turbine engine, specifically the turbofan, which is custom-built for flying modern airliners at Mach 0.8.
Which brings us to Section 3, the gas turbine powerhouse, the engine that completely revolutionized commercial airline travel.
Just look at the sheer size of the fan blades on the front of this turbofan. Early pure turbojets had some major issues with noise and fuel consumption because they forced a huge acceleration onto a very small amount of air. The turbofan solves this brilliantly. Those giant front fans allow a massive amount of air to just bypass the hot core of the engine entirely. That bypassed air produces about 80% of the total thrust. The result? A much quieter engine with way better fuel economy at airliner speeds.
Now, unlike that piston engine, where everything takes turns happening in the exact same chamber, the turbine engine uses a continuous flow cycle. Completely separate sections of the engine are devoted to the air inlet, compression, combustion, the turbine, and the exhaust. All of these functions are happening simultaneously, without any interruption, accelerating a continuous mass of air straight through the machine. The real secret sauce for extracting thrust from this continuous flow, Bernoulli's principle. By using convergent ducts in the exhaust section, the engine takes the expanding volume of superheated gases and squeezes them down into a final high-velocity stream. Thanks to Newton's third law, shooting that massive high-velocity air out the back creates an equal and opposite reaction that violently thrusts the aircraft forward.
Moving to Section 4, breathing, fueling, and starting. Because an engine on its own doesn't do much without its support systems.
An engine is basically useless if it can't breathe, right? Notice this complex induction system acting like the windpipe of the aircraft. Because a gas turbine gulps down considerably more air than a piston engine, the inlet design is hypercritical. The air entrance passage has to conduct incoming air to the compressor with almost zero turbulence. These systems often use advanced engine barrier filters, which significantly cut down on the dangerous ingestion of foreign object debris, or FOD, into those delicate compressor blades.
And waking these beasts up from a cold, dormant state, totally different challenge. Unlike a piston engine that just needs a relatively quick little turn to start firing on its own, a turbine has to be accelerated to massive speeds first. You literally have to generate enough continuous airflow through the compressor before fuel can even be introduced and ignited. Otherwise, the engine just won't start.
You can see right here just how wild the internal gearing of a turbine starter actually is. Because of the insane power required to spin up the high-pressure spool and all those giant internal compressor blades, these starters are heavy-duty electromechanical or fuel-air combustion devices. They draw huge amounts of energy just to overcome the resting inertia of the turbine and carry it all the way up to a self-sustaining speed.
Finally, let's hit Section 5, pushing the limits of flight. Let's look at the future of aviation engineering. Because the engineering absolutely never stops, right? We're constantly trying to reduce dangerous emissions, especially oxides of nitrogen, or NOx. Since most NOx is formed by oxygen and nitrogen reacting at extremely high temperatures, modern research is heavily focused on the combustion section. Engineers are figuring out how to burn that fuel-air mixture at much cooler temperatures without sacrificing an ounce of power. Enter the TAPS combustor design. It premixes the fuel and air using high-energy swirlers before the mixture even reaches the combustion burner area. It is absolutely fascinating how simply manipulating the physical swirl of the air creates a more thorough, leaner mix. This lowers the internal temperatures, dramatically cleans up the exhaust, and just makes flying greener for everyone.
So as we manage to squeeze every last drop of efficiency out of both our reciprocating pistons and our massive gas turbines, constantly dropping specific weight and cleaning up emissions, it leaves us with a pretty massive question. Have we actually reached the absolute physical limits of internal combustion and continuous flow designs? And if we have, what exactly is the next massive paradigm-shifting leap in aviation power going to look like? Think about that the next time you look out at the wing. Thanks so much for joining me on this explainer, and I'll catch you next time.